Hello everybody, welcome back. First thing to point out is you'll notice I'm jumping forward to section 4.4. That WebAssign homework was over 4.4 and 4.5, but due to the time-consuming nature of delivering the material to you in this way, I needed to cut the course down more to essentials. And so I cut 4.4 and 4.5 down to just part of 4.4. In fact, we're only going to really have you do exponentials. There is some nice material in there about gammas and bibles, and those are important, but for this course I wanted to trim it down. Now what that means is the WebAssign homework for this week is quite short, so you shouldn't have too much trouble getting that done, and I want you to go ahead and do that this week. So that 4.4 WebAssign homework is going to be due Friday, and section 4.3 over the normal distribution, I'm going to be introducing multiple videos. I think it'll take 2, maybe even 3 videos to really do the normal distribution justice. So I'll be feeding you that material over the course of the week and maybe the beginning of next week, and then that will be the WebAssign assignment that's due next week. And then the next written homework will come after that. Now, the exponential distribution, let's look at what that's going to look like. This is actually something that looks like an e to the minus x. So an exponential distribution is going to start high and then go low like this. And now, of course, the area underneath needs to be 1 because it's still a probability distribution. And we have some scaling that can happen. So we have some scale parameter. So what the scaling is going to do is that scale is going to go in front and then also up there with the x, which means that's a horizontal stretch or shrinking. And if you remember your algebra / pre-calculus, when it's in there with the x, it does opposite. So a large lambda is actually going to squeeze in my horizontal axis, and then it's going to stretch it higher. So a high lambda value is going to make the distribution start up here and then come down lower quicker. And then a low, so this is high lambda, and by high I mean bigger than 1, and a small lambda is going to make it start vertically lower and then take longer to stretch out. So this is a low lambda, or something less than 1. And now I want to talk real quickly about the main sort of application where these appear, and that actually is in our Poisson processes, which is why I thought of this one as being essential. So what we would call a Poisson process. So say we have a Poisson process with the events occurring at a rate. There's a difference here between how we introduce the Poisson distribution, and I'll talk about that real quick in a moment. We did an example where we looked at the rate of something happening in the homework on that section about Poisson distribution. So we have our events occurring at a rate, and let's say that rate was lambda. Then the gaps of time between events follow an exponential distribution with that lambda. So for example, say we had a Poisson distribution where I was looking at a period of, well, I don't know, 5 years. And then the Poisson distribution, we had some average number of time. So Poisson distribution. we had some average number of times the event would occur. So let's say it's, I don't know, 7 of them. So let's say our mu for the Poisson is 7. If that were the case, what I could do is say, well, what if we don't care about this specific time period of 5 years? What if this isn't a kind of event that just happens over time, all the time? And so I could look at this. The Poisson process idea is we just look a long time, forever and ever, and these events still occur at some sort of same average rate. And then as we move forward through time, we have some average rate that these things are occurring. Now, what is that rate? Well, on average, I'm occurring 7 times every 5 years. So my rate here would be 7 times in 5 years would be 7/5 per year. And so what that means is that, so the gaps, how long after this event occurs do I expect to wait until the next time it occurs? That would be an exponential distribution. So we're moving forward through time. I have one of these events occurring, and I want to look at how long before the next one happens. That would be exponential with this lambda. And so this shows up a lot in product failures, lightning strikes, whatever. Whatever sort of thing, actually, if I was to look at a fixed chunk of time would occur in a Poisson distribution way. I could actually look at length of time between occurrences in an exponential distribution way. So for a continuous random variable, the exponential actually connects very strongly with one of our discrete ones, the Poisson distribution in particular. Now, let's build up our formulas. So the exponential distribution. Let's make a formula list. So what is this curve? So my density function, well, I can't have negative gaps of time. So that primary application tells us this thing wouldn't make any sense for less than 0. So there's 0 probability density for x's that are less than 0, or less than or equal to 0 for continuous random variables. It doesn't really matter. So nothing's happening until I get above 0. And then finally my probability function is going to jump, and then it's going to follow this e to the minus x kind of shape. And it's going to have that scaling happening. So it'll be lambda e to the minus lambda x for my x's that are not negative. So that's our density function. That's our distribution we're looking at. And you could check, although it would involve an integral that goes off to infinity that would have a limit in it. We saw that in the previous section, that can be handled, but it's a bit tedious. The area underneath that curve does end up being 1 because we're scaling vertically and horizontally in opposite ways. Okay, so now once we have that, my expected value, or my mu if you prefer, turns out to be 1 over lambda. I think maybe we will derive that, do the calculus, but I'll save that for the end of the video. So if you don't want to spend a bunch of time watching Mr. Cotton do a computation, you don't have to. So we'll push that to the end of the video. We'll derive these. And then my variance is actually going to turn out to be 1 over lambda squared. Now, when we compute probabilities with these continuous distributions, we have to do integrals. And if I have to do an integral, it's way easier if I already know what that cumulative distribution function is. When I do these probabilities, if I want some probability from A to B, then what I end up doing is integrating from A to B on this density function. And then, of course, fundamental theorem calculus tells me that's going to be some big F antiderivative fb minus f of A. And as we've seen before, cumulative distribution functions, the antiderivative that we want to use for these probabilities is all the area off to the left of whatever number. If I already know that area, then I can actually just plug these in, subtract them, and jump to this step and not have to do a new integral every time I want to do one of these. So we want a cumulative distribution function. So let's derive that really quick. And that I do want you to see, because being able to do an integral of just a basic exponential function should be expected. So let's say we want the cumulative distribution function. So let's call this big F of x, and it's going to be piecewise defined because my original distribution, let's just draw it right here, starts up here and it has nothing until I get to 0. It just stays 0. In other words, area underneath the thing, I'm not getting any area until I start getting to here, and then once I'm past 0, I'll start getting some area. So my cumulative function is going to stay at 0 for my x is less than 0. And now let's do that integral and figure out what the next piece needs to be. So if I wanted a cumulative distribution function, I'm not getting any area until 0, so I may as well say, okay, 0 there, and then I'm going to integrate up to whatever x value, and then it's going to be that exponential distribution, which is lambda e to the minus lambda, and now I need to use a different variable since we have the x's in our bounds here. And let's figure out what this is. So the lambda here is just a constant, so I can pull that out. So I have lambda integral 0 to x e to the minus lambda y dy. And now if I want to do an antiderivative for e to a number times my variable, what's the antiderivative? We divide by that number. I went over that in the last video. Oop, that would still be there. So my antiderivative that I would use here is going to be e to the minus lambda y divided by minus lambda. And of course I'm going from 0 to x. And now maybe I should pull this minus out in front, but I'll do that in the next step. So okay, so I have a lambda, and now here's in my antiderivative, so I want to take that, I'll pull the negative out in front, with the x plugged in, so we have e to the minus lambda x here, and then I pulled the negative out in front, so we just have lambda on the bottom, and then minus what I get when I plug in the 0, so that would be e to the minus, we still have that negative out in front, e to the minus lambda times 0 divided by lambda. Now let's clean this up. So I've got lambda times this piece here is just going to be minus e to the minus lambda x over lambda, and then I have minus negative, so that'll cancel off for us. So I have plus, and then e to the minus lambda times 0 is just e to the 0, which anything to the 0, that's just going to be 1. And then I have over lambda. And now this lambda that I'm multiplying by outside of the parentheses is just going to cancel these off the bottom. And then I'm getting 1 minus e to the minus lambda x. And so that's our cumulative distribution function, which is going to be very useful for us. 1 minus e to the minus lambda x for x's that are bigger than or equal to 0. This also equals 0 at 0, of course, which it should if it's sweeping out those areas, because e to the 0 is 1, and so 1 minus 1, that would give me 0. So this works out okay. This lets us do our computations fairly easily. If you know the cumulative distribution function, you can save yourself a lot of time, not have to do all those integrals. So, for example, if something was an exponential, say my lambda was 5, and I wanted to do a probability from, I don't know, x between 2 and 7, then knowing that cumulative would let me, instead of doing integrals, just jump immediately to, oh, well, if I want the area from 2 to 7, well, that's just going to be my cumulative function at 7 minus the cumulative function at 2. And now that we know that cumulative function, I can say that's 1 minus e to the minus, what was my lambda? That was 5. So 5 times 7. And now minus my big F at 2, which is 1 minus e to the minus lambda, which was 5 times 2. And then, of course, I could, let's Let's get this old stuff out of the way. And so then, of course, I could clean this up a bit. I have 1 minus 1, so that's going to go away. And now I have minus this, minus negative this, so that'll clean up to the one over here is positive, so I would have e to the minus 5 times 2, which is 10. And then this one had the minus in front of it, so minus e to the minus 5 times 7 would be negative 35. And then whatever calculator it will give us there. Anyway, now that we know that, we have the cumulative distribution function, we can do our calculations very efficiently. We have everything we need for an exponential distribution to work with the probabilities and work with our expected values of them and work with our variances. This is all pretty nice. So this is really all you need, and a pretty good place to stop. It's all I'm going to do from section 4.4. Now, a couple things that are mentioned from section 4.4 is what if I wanted a distribution that didn't start high here and come down? For things like, I don't know, the life of a machine, maybe your quality control is good enough that breaking down immediately is more rare, and you wanted a distribution that looked more like, okay, it's less likely there, and it comes up and then fades out like an exponential. This could be handled by something like a gamma distribution, which is mentioned in that section, and you can take a look if you're interested in how that would go. Another one is, what if I have something that maybe the likelihood is such that it sort of is very unlikely it breaks immediately, but then clusters around some sort of median and then it fades out like an exponential. This would be what would be called a Weibull, where it kind of looks like a bell curve, except you still can't have negative stuff. And those are very, very common and very useful as well. And so there are other models and other formulas that will capture these sort of situations. But I think for a good introduction, the exponential is the one that I wanted to include now. Anyway, that's a good place to stop the lesson, so thank you all. However, now, for this part of the video, I want to derive the expected value and variance for this distribution, for those who are interested in seeing it. So the expected value of this exponential is going to be, I'm going to integrate, now this thing runs from 0 off to infinity, so I have to integrate from 0 to infinity on this lambda e to the minus lambda x, except now I'm doing a expected value, so there's another x out here. So let me clean that up a little bit. So let's say it's that number lambda x e to the minus lambda x. Now we're doing expected value. I have an integral that's going off to infinity. How do I handle that? Well, we'll take the integrals up to some bound. Let's say b, I don't know. Or actually, let's do t. I'll call it t. We'll do these and then take the limit of the area as that gets bigger. And so I'm going to mark this as, this is the limit as t goes to infinity of the integral from 0 to t of lambda x e to the minus lambda x. Now we have some difficulties here, because what's going to happen is I can pull out this constant. That helps a little bit. But how do I handle an integral of something like x e to the something x? This actually will require integration by parts, which some of y'all's Cal 1 class might have covered that, and some might not have. If you've gotten through by Cal 2, then you definitely have seen that. So I'm just going to run that really quickly. So if you're not sure what I'm doing there, you can always look up a little tutorial on integration by parts. So what's going to happen here is we need one of these parts of this thing that's going to go down in power. We're going to take a derivative, and another one that we're going to take an antiderivative of. And now if I take a derivative of something times x, then the x drops off, which makes this nicer. And if I take an antiderivative of e to a number times x, it's just a number that pops out. So it doesn't really get any nastier integral-wise. So for my integration by parts, I want to let my u, the thing I want to take the derivative of, I'm going to let it be lambda x, so that my du is going to be, the derivative of that is just going to be lambda dx. And then I'm going to let my dv, the thing I want to take an antiderivative of, be that e to the minus lambda x. And then I'm going to let my v, the antiderivative of that is just going to be, well, the antiderivative of e to the minus lambda x will be negative e to the minus lambda x over lambda, as we saw in the other example. Okay, so what's that going to turn this integral into? We're still taking this limit in the end. Limit as t goes to infinity of, now we've got a big mess here, u times v. So we'll have minus, now this is still an integral, but we can put the bounds on the pieces separately. So my uv is going to be, we have lambda x times this thing. So minus lambda x e to the minus lambda x over lambda. Those lambdas will cancel, so that's nice. And this is going to go from our bounds that were on that integral, so 0 to t, and then minus the integral of v du, which we have a minus here, which will cancel that, turn that minus into a plus, and then my v du, so now we want to multiply this times this, so those lambdas will cancel, but I'll go ahead and write them here at the moment, e to the minus lambda x, and then dx. And then this integral is running from 0 to t. Okay, so let's clean that up. So I'm looking at a limit as t goes to infinity of these lambdas canceled, and I'm going from 0 to t, so we have minus e to the minus lambda t minus negative, so plus, and now if I plug 0 into that, I got an x right there. That just is going to be 0. And then we have plus this integral here now, but those lambdas are just going to cancel, and I just have an antiderivative for e to the minus lambda x. So that's just going to be plus e to the minus lambda x divided by minus lambda, so a negative is going to pop out. And then from 0 to t again. Okay, so let's clean this up. So I'm looking at a limit as t goes to infinity of minus e to the minus lambda t, and then we got to expand out this part. So if I plug in the t, I've got minus e to the minus lambda t over lambda. And then if I plug in the 0, we've got minus negative, so it'll become plus. And if I plug in 0, it's going to be 1 over lambda. Now, this doesn't look like that expected value, does it? The 1 over lambda is what we're supposed to get. So what's going on here? Well, we haven't taken the limit yet. Now, e to the minus, like an e to the minus x, or e to the minus some positive number times t, what's that going to look like? The graph, if you just think visually, looks like this. As t goes to infinity, it's getting smaller and smaller. And so this is going to disappear. And so is this. So finally, we take that limit, and yes, we get 1 over lambda at the end. Okay, so now suppose we want to do the variance, which is expected value of x squared minus expected value of x squared, using our usual formula. We already have what expected value of x is, so now I just need to take expected value of x squared, which will be an integral from 0 off forever of lambda x squared e to the minus lambda x. And so this will take an integration by parts again and a limit. So we're going to have, this is limit as I go further and further of the integral from 0 to t of this thing. And now I can let doing an integration by parts, I can let my u, the thing I want to take the derivative of, be the lambda x squared. Then my du is going to be the derivative of that, so that would be 2 du equals 2 lambda x dx. And then if I let my dv be that exponential part, then I have the e to the minus lambda x there. And then my v, the antiderivative of that, is going to be minus e to the minus lambda x over lambda. And now, of course, the formula again is uv, and of course that's going to go from those bounds, minus integral, same bounds, v du. And let's put that all together. My uv here, if I look at what those things are, is going to be, and now we still have this limit as t goes to infinity. My uv is going to be, the lambdas will cancel, we'll have minus x squared e to the minus lambda x from 0 to t. And now I have minus integral v du. My v is minus e to the minus lambda x over lambda. And then my du is 2 lambda x dx. Now let's see what happens here. So we're going to get the limit as t goes to infinity of this from t to 0. Well, if I plug 0 into that, it's just going to equal 0 because the x is out in front. So this will just be minus t squared e to the minus lambda t. And now this negative I can pull out in front, so we have plus integral from 0 to t. So plus integral from 0 to t of, these lambdas will cancel, and I've just got 2x e to the minus lambda x dx. Oop, that's supposed to be a t. Okay, so now let's look at this. As t goes off to infinity, notice here that this thing looks like a minus t squared. To get rid of that negative exponent, I could think of it as having e to the positive lambda t on the bottom, but now this thing on the bottom is exponential, and it's just a polynomial, a quadratic thing on top. So the bottom's going to blow up faster when t gets big, and so this whole thing will get smaller and smaller and smaller and disappear. So in particular, I know in the limit that this thing is going to go to 0. So I can go ahead and say this is the limit as t goes to infinity of just this thing here. Integral from 0 to t of 2x e to the minus lambda x dx. And now, instead of running an integration by parts again, what can we do? Well, this looks really close to the integral that we did for the expected value. In particular, let's get rid of that limit and just say, okay, let's say integral from 0 to infinity of 2x e to the minus lambda x dx. Remember, the expected value was the integral of x times that original density function. So we had lambda x e to the minus lambda x. What that tells me is if I can get what's inside there to look like this, in other words, if I pull out 2 over lambda, then what's going to be left is going to be integral from 0 to infinity. We pulled out that 2, so it's not there anymore, but I pulled out 1 over lambda. So what's that going to do? I need a lambda on top that would have canceled with. So that gives me that lambda that I needed. Right? This lambda on the bottom would cancel this one on the top here, and then it would go back to being what I had. And this thing right here is just expected value of x. So my 2 over lambda times my expected value of x, which was 1 over lambda, comes out as 2 over lambda squared. And so this is our expected value of x squared. So my variance, so my variance is expected value of x squared minus expected value of x squared is going to come out as 2 over lambda x, or lambda squared, sorry, 2 over lambda squared minus my expected value of x, which was 1 over lambda squared. And so I've just got 2 over lambda squared minus a 1 over lambda squared. And then when I do that subtraction, we have 1 over lambda squared. And that's what it was supposed to be. So if you wanted to see that, there it is. Thank you all.